Thank you very much, Francesca. Well, I should also like to say a couple of words as an introduction following the mayor. Actually, I've been with this Euromec Council really for a long time. So George Batchelor, who was a founding father of this idea of the Euromec Colloquia, invited me to join the council long time ago, and there are a couple of these sort of ideas from this very first beginning. First, the Euromec Colloquia were organized because there was a need for a format for such kind of discussion where the problems were really very much focused, so that the audience should be all around this sort of area, and this is something that was absent in Europe in the 50s or 60s, and now we are it's 563rd the colloquium, and then there was another idea from these years where these ideas were elaborated, that this sort of format, I mean the colloquium, is not just simply to come and to give such kind of brilliant talk with final results and all that sort of things. This possibility that this community understands the problem, this creates a very good ground for discussion, so that the problems could be also open, and the problems could be somehow, in not on the final stage, but just to get the discussion. And that is exactly what is needed, and that is our colloquium is exactly about these metamaterials, and as we have understood that it is also very important for the town, and this is something that is going on very well. Well, now metamaterials, this is a focus, and actually what we have understood yesterday and this morning, this is not only the technological materials, man-made and very complicated and all that. Nature is a master to create metamaterials, whether they are bones or the arteries or horns or shells or whatsoever, and these are very complicated structures, and if we could understand the mathematical models and could understand what is going on with our this sort of mathematical theories, this is the way to understand. And this is a way we can also understand that maybe the examples from the nature could be used also for something that the contemporary materials. Well, I'm going to speak about this on solitary pulses in cylindrical biomembranes, and actually the idea is here very simple, and I'm not going to give very complicated mathematical models or just such kind of explanations. The main point is that how these action potentials in nerve fibers create also mechanical waves. And the experiments show that this is what happens, and then there is a mathematical model derived by people some years ago, and we picked it up and tried to analyze it from the viewpoint of wave theory. And just to modify the model in order to get the better results. Well, and the point is actually here that the nerve pulse is really a solitary pulse, but it's not a soliton. It's a solitary pulse, a very special asymmetric pulse, and this is measured in millivolts. It's could be the amplitude could be about 100 millivolts, and the time scale is here given in milliseconds. It has got a very special shape, the asymmetric shape here, and the certain overshoot. That this is very important from the physiological viewpoint. And the mechanism is that the nerve fiber is actually like a cylindrical biomembrane, and the pulse actually is governed by the ion current through this membrane. The sodium and potassium ions are the most important, and this is actually the membrane. It has got a very interesting properties, so that it's all or none phenomenon, so that the very small excitation will disappear, and if an excitation is above a certain threshold, then the pulse will be formed, and there is a refraction length here that says that the next pulse can't start from here. It must wait until it's almost the equilibrium is restored, and then the next pulse could follow. And the pulses, when there are the head-on collision, something like that, then our usual understanding is that the waves could penetrate each other, but in this case the waves will be annihilated and then nothing will happen, and this is the typical reaction diffusion system. So the structure of this membrane is pretty complicated. So it's made of lipids, so that this is internal, where the interstitial fluid, and then along that the pulse will propagate, and this is the lipids which are lipids and proteins together, which form this cylindrical membrane. And if we go to some kind of better picture, not the scheme, then we shall see that this membrane is composed in such a way, and the action potential is going along that side, and through the membrane, the ion currents keep it going. So that this is the usual procedure, and now the problem is how to model this sort of process. And it was in the 50s, last century, when there was the very special models derived. First, it was the Hodgkin-Huxley model. This is a classical model. I'm going to show it. And then the later, what is also pretty well known, it's a Fitzhugh-Nagumo simplified ion current model, and then about also some 20 years ago, I also tried to get the evolution equation for such kind of action potential, which is actually the electric pulse. So that one should start from the 1D telegraph equation, just in the full form, but usually the inductivity is taken 0, and then but here is one term more, and this is related to the ion current. And Hodgkin and Huxley, actually what they did, they used this telegraph equations with inductivity neglected, and the result is a parabolic equation. Parabolic equation, as we all know, that it has got the infinite velocity, but in this case there is an ion current, this term, and this ion current is highly nonlinear and includes some kind of, as they called it, Hodgkin and Huxley, phenomenological variables. In our terms, we could say also that these are sort of internal variables, and so that this ion current these phenomenological variables should be also determined. There should be some kind of governing equations, and what was the main result of this Hodgkin-Huxley model? That they proposed some kind of kinetic equations with a very complicated empirical expressions from the equilibrium states and naught and so on, and with the relaxation time tau n, tau m, and tau h. And then for the very simplified model, the Fitz-Yonaguma model is just one equation like that. If you integrate it once with respect to t, you get this integral term from this v here, and you see that it's exactly the same sort of parabolic equation, but with a special this additional influx of the energy. And what I did, it was the evolution equation approach, so that proposing some sort of velocity going to the moving frame, getting then the first approximation, and if we take this sort of only one ion current, then the result is a sort of evolution equation, which is when you go to the steady wave, and then this is a linear type of equation, highly nonlinear, and then certainly the velocity is dictated by the properties of this function. This means by the properties of the ion current. Well, that's it. That's the story. And then usually this is carved on the Hodgkin-Huxley model is like carved on the stone tablet. But is it only the action potential? But the measurements show that there is also a mechanical wave and the heat production accompanying the nerve pulse propagation. And so this is the experimental picture. It's Tasaki, 1988, and this is the top one is the displacement, transverse displacement of this biomembrane. It's not the picture was not so very good, but you see that it goes up here and goes down here, and the pulse is quite typical, like this Hodgkin-Huxley configuration. The first. This part, the pulse itself, and then the refractory tail here, because this is here the equilibrium. And so this is not the only experiment. There are several experiments. Some years ago, for several the squid, which is the traditional object, parfish, even for nerves extracted from frogs, and they all show some sort of mechanical displacement, which is actually measured in nanometers. So it's only something 2 or something like that nanometers. So it's really very small, but nevertheless it exists. And now the question is how to model it. What could be the mathematical model? And then several years ago, Heimburg and Jackson have proposed a model for a mechanical wave. So this is the scheme, and they based on that on the density changes in this cylindrical biomembrane. And the basic equation they took very simple. So it's a usual wave equation like here, but what they proposed is that the velocity actually depends on this density changes, so that the density change is marked here u. So that this was the first assumption, and the second assumption was that they had one term just to get dispersion, but this was just it was made by physiologists, and so we would like to have a dispersion. Well, we add this term, and then we get this nonlinearity and dispersion, and actually this comes to the Boussinesq type of equation. And if we take this sort of assumption here, then usually for the nonlinear waves in solids we have this sort of the gradient du dx, but not the displacement or the variable itself. And the equation, what they proposed and solved was like that. These coefficients, they got from some kind of experiments. P is usually negative. I'm not going into these details. And then they took the dispersion coefficient H, well, just simply to get some kind of results. Certainly it's possible to get it into the dimensionless form, which is more, it's better for calculations. And what they have shown that there really could be, as a result, finding the steady wave solution for this equation, they got some kind of this solitary pulse. They called it soliton, although they didn't check that whether this is soliton in this way. It's a solitary pulse. But if you now think about these coefficients, what they have proposed, and look here, it's from their paper 2005, so that this distance is given here in meters, so it's about 10 centimeters. Well, then it seems that it's a little bit too long, but it's a model equation. And now if we think about that it's a longitudinal density change actually, and transverse distribution is different. And certainly that when we take now our knowledge from rods, from example Alexei has explained it in his book a couple of years ago very clearly, that the transfer displacement actually is related to the longitudinal displacement. You should take the gradient, and this coefficient is usually radius, the running radius, and then so on. And in this sense, if we now just simply, if U is a soliton or a solitary wave, then the derivative is just exactly something qualitatively just the same what was measured. So that equipped with such kind of understanding, we tried to also to understand what is going on, and what we would like to add another term here, because the dispersion analysis showed once there is only this sort of fourth derivative, the velocity will be unbounded. And this is something that you can work with the smaller velocities, but physically it seems to be that from our knowledge from microstructures, then the knowledge from the theory of rods, as Alexei has put it, and so that should be certainly a little bit more complicated model for that. And in this case, that if we solve now this equation, you really can get this sort of, you start with some kind of solitary pulse, and then you get also these first derivative, I mean the transverse displacement, if we call it so, something qualitatively the same as it was in the experiments. These results were obtained by using the pseudospectral method for solving such kind of equation. It's not so very straightforward. The first works, we have applied the pseudospectral method for several problems, like for evolution equations, for the KdV or Korteweg Breach type equations, or for the Boussinesq type equations, so that is two-wave equation. So that this is something that we can really understand that what happens. But now there is quite an interesting problem that we are also related to this the analysis of solitons, and if you are able to produce an initial excitation exactly in the form of the steady wave, okay, it will propagate. But if not, then this will the initial excitation will form some train of solitons. So it will be just according to the energy embedded into the dictated by the coefficients, and then some kind of solitary the train of solitary pulses or solitons will emerge. And so what we try side, actually, is also that following then these experiments, trying to understand how this sort of modeling will give you these solitary waves, like Heimburg and Jackson have proposed. If we take now only this nonlinear part and neglect the dispersive effect and take it into account that P is negative, then you see that the discontinuity will be formed not in the direction of the propagation, but here in this side. Usually we have this if we have the something like here, just for the comparison with the deformation gradients, then certainly it will be different. And now it's quite interesting that actually that if we start with such kind of numerical calculations, and well, we start with a certain pulse, which is, well, somehow the parameters, the width and the amplitude are, well, just chosen for the model equation. Then the point is quite interesting that the result, the balance of the dispersive effects and the nonlinearities start to form not here in this part with in the direction of the propagation, but with this back side, and so that after a certain period you can get it that just a very nice train of well, solitary waves, and we are not sure yet whether they are solitons or not, because you always have to check it the elasticity of interactions. But this way or another, the point is that if we use such kind of model, which is very simple, then this ad hoc modeling could give you really some kind of these results. But I think that we actually have to really to return to that situation and to understand how this sort of structure will behave if there is some kind of some kind of excitation from inside. So this is an action potential, electrical pulse, which will cause the changes, mechanical changes in this cylindrical biomembrane. We can use certainly the several our parallel models. Come to the end again. And there are many such kind of problems, because we are now looking for the suitable dispersive model based on the structure of lipids. So that it's the problem of the molecular dynamics. If you have got very simple molecules, then it's known. But this is a very special structure with these hydrophobic tails, and one should be very careful how it actually deforms under certain excitation. Then the next problem is really one should unite the models of the action potential and the mechanical wave. There are a couple of these considerations. The famous paper by Gross and others some years ago has well analyzed it in qualitative way, whether it's the electrorestrictive process or piezoelectricity. For piezoelectricity, again, Gerard has proposed some of the models, and then certainly the heat production, as also was measured by the experiments. So the thermodynamics of pulses should be understood. We did it also several years ago with Gerard. It's a thermodynamical viewpoint on nerve pulse force dynamics, and the idea was just to generalize this Hodgkin-Huxley and Fitzhugh-Nagumo models and to find dissipation potentials for them, because it is something that it was not used by this in these classical theories. We tried to understand how this dissipation potential will be realized in terms of when these phenomenological variables are treated like internal variables. But the next step should be done now. The fluxes should be calculated from the dissipation potential to understand whether this heat production, which is also it's a very small, but nevertheless it exists and is measured. So that, ladies and gentlemen, this is an extremely interesting problem. It's a very special metamaterial in this sense that this is the sort of made of on the molecular level. The effects are pretty small. What are measured? These are in the order of nanometers, but nevertheless they exist. And then to understand this process, really to get into it, it's really a fascinating problem. So I think that this is all what I wanted to tell you. Thank you for your attention. You could see also here our work on the whiteboard.
Yeah, how about validation by experiments? How do we really know which model is correct?
Yeah, well, certainly that's a usual problem. We know the experiment. We are not able to carry on experiments ourselves. We have the experiments with the heart cells, but the heart cells are quite different, and the main point what we are interested in is in diffusion, so that we are familiar with the problem, but not with this problem, because these are made a little bit in a different way. But the transport through the membrane, this is something that we've been studying also experimentally.
One more question. What about the effect of the change of thickness of the nerve on the
as you have seen that these are homogeneous in this sense. So that this is something that I've been thinking, but I haven't found any such kind of good explanation, because you are absolutely right, because it's really changing. And then what is the influence of these Ranvier nodes and all that? So it's real. Yeah. Yeah.
About this mechanical determination in the neuronal cell, do you expect that the rate independent approximation would be good for such a process?
Well, the main point is actually it's a coupling. The coupling from the action potentials, because you can't imagine exactly intuitively that you have got the mechanical wave propagating. It starts from the action potential. So the coupling should be, I think, that the electrostrictive mostly, and then we would like to really understand that to solve these let's say two governing equations together, and to initiate certainly the sort of action potential in the electric parts, but mechanics is there. So these are the many experiments. Actually, I showed only a couple of them here, but these are measured and these exist. So that this is actually like a challenge to understand that I don't like these ad hoc models that let us assume that there is a one term added. That I would like to understand exactly, as for example, like Gerard did, that the bone starts to grow because we can understand exactly that what are the changes in these all these forces and also how the deformations change.